All right, so here we have the first two lessons from a section in the textbook focusing on how we can represent functions in different ways. In general, this is like all the first parts of this unit, or most of the first parts of this unit. This is meant to be predominantly review, although the types of questions and some of the details may either be new or feel new. That's it. What I have here is a function, and it's a graph of y equals f of x. And so I'll just kind of label it like this. And so I can see this function. It's just, it's been just given to you as a graph. First, I want you, how can we show that f of x is a function of x? Really means, how can I show that this is a function? Now, a few things before I get into that. Anytime you see an equation in function notation, like this, or this, same thing, essentially what we're saying is we're formalizing that whatever's inside the brackets is the independent variable. So that's what goes in, that's the input. And whatever letter we have here, that represents the dependent variable, or the output. So in this case, we put in let me say that again. We put in x, we get out f. And if something is a function, you put one number in and you get one number out always. You never put one number in and get two numbers out. So how can I show this is a function? Well, hopefully you recall the vertical line test. And this, what you see here, we say passes the vertical line test. So let me write that down first. So I'll say that f of x because like I said, if something is a function, that means if you put one number in, you get one number out. Never anything different. You never put one number in and get three numbers out. And so if I look here, what do I mean by that? Well, the numbers that go in are the x, right? That's the independent variable. And so my x-axis, those are the numbers that go into this function. And what comes out is the y-axis, y equals f of x. And so if I look at this, there's never a point where for one x value I have two y values. For example, right here, if I look at this vertical line right here, when x is -1, here we got an announcement.
Sampson, call parked on 801. Ms. Sampson, call parked on 801.
If I look right here, when x is -1, that's an open circle, so we don't look there. When x is -1, y, the output, is +1. There's never a point where when x is any particular value, there'll be two outputs. Hopefully this vertical line test sounds familiar. It goes back to grade 10, and it's a nice, easy way to tell visually if something is a function if you can visualize the graph. In this case, I've given you the graph. So that's it. Regardless if something is a function or not, you can describe its domain and range. And so what's the domain of this function? That's a way of describing all the inputs, all the independent variables. And in this case, the domain, if we look here, it starts at -6, but doesn't include -6. There's also a hole right here at +2. There's a pointed discontinuity at 2, which means this function, when x is +2, there is no output. So +2 is not part of the domain, and it ends at +4 and includes that. So there's various ways I can describe it. I'll describe it in two different ways. So one way of describing the domain is to say that -6 must be less than or equal to x, which must be less than or equal to 2, comma, and 2 is less than x, which is less than or equal to 4. So what I just wrote down there is perfectly valid. Again, the first part right here kind of takes into account this region all the way to here. I've highlighted in yellow. And this part right here takes into account this region I'm highlighting in green. That's it. That's called set notation. We can also use interval notation, which I still have to write as two different chunks. And so in this case, it would be round bracket -6, comma 2. That's the part in yellow. The round brackets indicate that we don't include that value. And then as well, what I've highlighted in green would be 2, comma 4, but a round bracket and a square bracket. That's it. You could just say, put a comma here. You could say and. Give me a word if you want to look really fancy. You put this symbol here, which means union, which essentially means and or both. And again, I'm just writing that down because you tend to see that in the textbook. But these are both good. Don't get too hung up on notation for this course, but I do want you to understand what you see in the textbook. So there's the domain. The range is a description of the outputs of a function, or anything. In this case, the range is from -4 to 5, but not including -4, including 5. I can definitely see 5 is included, and everything in between. So the range is from -4 to 5, so I can either say -4 is less than x is less than or equal to 5, or I can say round bracket -4, comma 5, square bracket. Okay, same thing, different notation. Okay, evaluate f at -2. Well, that means I want to look at my equation and think about when the input is -2, what's the output? Well, sorry, I said look at my equation. If I had an equation, I could look at my equation, but I have a graph. So if I look at -2 on the input, that's right there. And so what's the output? 4. So f at -2 equals 4. And other way around, determine x such that f of x equals 5. So in this case, I'm trying to figure out the input so that 5 is my output. And so look at my graph. Where is 5 my output? Well, in these two places. Both those places I've highlighted in purple have an output of 5. So when, in this case, when -3 goes in or when +4 goes in, 5 will come out. And so you can say when x equals -3 or 4. There's two solutions to this. All right, with that said, the last question is based on some actual data. And so what we have here is a scatter plot of some actual data, and I kind of took this from the textbook, in which it says the researchers measured the blood alcohol concentration of 8 male subjects after the rapid consumption of 2 standard alcoholic drinks on an empty stomach. So essentially, 8 guys were given 2 shots of alcohol without any food in their stomach. And over the period of 4 hours, the researchers took measurements of their blood alcohol concentrations. And this was what you see the average of it. And so, again, this is actual data. So on the x-axis, you can see it's time in hours. The y-axis, it's blood alcohol concentration in milligrams of alcohol per milliliter of blood. All right, so there's your scatter plot. And so then I say, let A of t represent the blood alcohol concentration, A as a function of time in t. So I'm just kind of formalizing. Let's call t the independent variable. Let's call A the dependent variable. And even though I have a scatter plot here, that's just discrete data, it's not a big task at all to sort of imagine what the curve of this would kind of look like. So it probably looks something like this. Essentially kind of connecting the dots with a smooth curve. Again, this is the average data from 8 different people. So that's my sort of sketch of what the graph of y equals A of t would look like. There's the curve. All right, that's it. My first question is determine or estimate t such that A of t equals 0.2. Okay, so first keep in mind, I know what A of t is. I don't know what t is. So I'm trying to figure out the time, essentially, upon which the blood alcohol concentration is 0.2 milligrams per milliliter. So here's 0.2. So I'll kind of highlight that in green. And so I can see if I look at that, clearly there's going to be 2 sort of times when their blood alcohol concentration is 0.2 milligrams per milliliter, which makes sense. First on the way when they're getting more inebriated and when they're getting less, when they're sobering up. And so if I look here, just a quick little estimate. Again, I can't be feeling like I can be exact with this, but it looks somewhere, I don't know, about there. I'd say if this is 1, this is 0.2, so about 0.1 hours. So 0.1, let's say approximately 0.1 hours. That's my first one. And then over here, let's say 1.8 hours. Again, I'm definitely estimating, but there's good estimates and bad estimates, and these are both, I think, decent estimates. Okay, from the data we have. My next question, when is A of t changing the fastest? Now, this idea is actually going to be an ongoing idea of this course, the idea of looking at the change of things and describing the change. I think here it's safe to say this is definitely changing the fastest at the beginning. That's when the line is the steepest. And so essentially, I'm going to focus on this sort of interval from here to here. From that first sort of stretch, actually, to be honest, if I want to even more detailed, I should probably even focus from like here to here, something like that region there before it starts kind of flattening out a little bit. That's when the blood alcohol concentration is changing the most. It's going up, but in this case, even when it's going down, it's never that steep. So I'm going to say, what is that? Definitely from 0 to about 0.4 hours. Right? If I just highlight, I'm looking at kind of this region here roughly. So what is it changing the fastest? From 0 is less than or equal to time, which is less than or equal to about 0.4. Again, I'm estimating, but that's definitely what's changing the fastest. This idea is it's going to become a key idea of the course, not so much when your blood alcohol concentration is changing the fastest, but when how things are changing. So then I said, say the researchers gave each of the subjects just one drink instead of two. On the same grid, what would this curve kind of look like? Well, the key thing is it would have to, I'll maybe draw this in purple. It would have to start at 0 still. It would still go up, but probably half as high. So I would say roughly to about here probably. It probably would take about the same amount of time to get to that point because you're given one drink instead of two at once. But then when it goes down, the key is that you should sober up faster. So roughly, I'll say roughly half the time, so something like this. So I should see some sort of curve like that. All right, last question is the same data, but now I made 2 regression models for each of the parts. And so what you see here is exact same data with in red and in green a regression model that I used Desmos to create. And you can see the equations. Okay, so modeling. So I modeled the first part with a quadratic equation. I modeled the second part with an exponential decay function. All right, so again, it's a model, but it's a decent model, especially for, the only part where it's kind of weird is where these 2 parts don't quite connect there, but that's okay, we can get the idea. And that's all, again, like I've said before, models are not meant to be perfect, they're just some are useful. And so with that said, use this regression model to determine the following. A at 0.1. That means, according to my model, the blood alcohol concentration of someone after 0.1 hours. So what the key is for that, I'm going to look at this first piece. I have an equation here in piecewise form. And I know I want to look at that first piece because I look at this first piece when time is between 0 and 0.5. And so for this, I'm going to go to that equation and substitute t with 0.1. So negative 1.433 times 0.1 squared plus 1.54 times 0.1. I know I'm looking at just that piece because, again, the 2 pieces are differentiated by that little restriction on the right-hand side. With that said, I can just go to my calculator. I don't really care too much about the number, but according to when I type this into a calculator, I get about 0.1397. What are the units, though? Milligrams per milliliter. All right, and then for the last one, I'm looking at 2.8 hours, roughly around here. And so I know I want to look at the second piece of my equation in piecewise form, because if you look at the restriction on the right-hand side, I look at that piece from 0.5 to 4 hours. And so I'm going to substitute the t in that exponential equation with 2.8. So I'll say this equals approximately 0.716. 702 to the power of 2.8, because that's where the exponent went. Minus 0.17. And again, I don't really care about the number too much. I get about 0.096 milligrams per milliliter. All right, so the focus of this lesson is really just familiarizing yourself with function notation again, understanding what the definition of a function is, and how to read piecewise notation here, and how to connect it to graphs. Lots of little things were reviewed. Well, with that said, I'm going to stop it here. Thank you.